an arbitrary location as 0 that you all of us agree as okay, this is our 0. Now if I give you 4, you know exactly where 4 is. Where is 4? It's, well, we only know one thing. We only know it's on the right side. But where is it along the right side? Do we know? Or what would you have to know for you to tell me exactly where 4 is? Yes, you need to know the scale. You need to. We need to know where is 1. If I tell you where is 1, then you can tell me where 4 is. Right? This is if you have single numbers, right? So you know this 1, 2, 3. You know this is 4. If I ask you where is minus 3.1, maybe you'll say it's maybe here. Okay? This we are familiar with, right? We are also familiar with the concept of let's say the size of a number, right? If I asked you, well, we can talk about the size of the number. Let's say in terms of forget about the sign for now. Okay, if I asked you whether 4 is bigger than 3.1, minus 3.1, you'd say yes, 4 is bigger because the absolute value of 4. Right? So this operation of taking the absolute value tell you something about the magnitude of the number, irrespective of its sign. For example, if I had minus 5, minus 5 is of course is a bigger number than 4, ignoring the sign. Okay, for now. Okay? And then if I gave you two numbers and I asked you how much is the separation between them, how would we find that out? Or what is the distance between them? Don't worry about the sign. How would we compute that? Let's say this is 2.5, and I asked you what is the distance between these 2 points? Well, you simply take the two numbers. Let's say this is x1, this is x2. You say, okay, take the difference and then take the absolute value, because we don't worry about whether it's to the right or the left. This is you and I would agree this is a reasonable way to measure the distance between two numbers. Okay? You could ask, why would we care about the distance between numbers? Well, we might care about the distance between numbers. For example, if you have a problem where, let's say, you're measuring, I don't know, blood glucose level, right? And those are individual numbers, okay? And let's say we have a bunch of measurements that are here, and these are all measurements taken from healthy subjects. So you would agree that most of them healthy subjects would all group together, right? More or less, right? Because all of us would have our blood glucose level taken at a particular point in time in a day would have more or less, I don't know the number, but yes, some number, right? The range. But if you're somebody who is diabetic, then you're likely that your measurement is going to be far away from what healthy behavior is like. And this is a place where you would be interested in a measure like this, right? What is the distance between two numbers would be very much applicable for problems like that, right? This is all in one dimension, and again, all of this seems extremely natural, right? This is the most natural thing to do. Okay, that's because we are used to this. Okay, but we don't necessarily only make one measurement in most cases. We make multiple measures, right? Now, how do we represent those measurements? Well, maybe let's say you're measuring n different numbers for a patient, right? That is where the idea of n vector comes. Okay, n vector simply means a bunch of n numbers, and the order matters. You always put them in the right order, and we will usually represent them in the notes and in the book. You'll see bold face small letters. Okay, because I cannot write bold on the board, I'll usually use an underbar. This essentially means I'm talking about a vectors. Okay, and we will usually represent them like this. There's a tall column of numbers, and n vector means there are n numbers in this vector, and we will represent them by v1, v2, vn. Okay, the subscript essentially tells you the position of that number. Okay, the I element of this n vector is vi. Of course, I is less than between 1 and n. Okay, and for now, let's assume each of these is itself a real number, and we'll represent real numbers like this. Now, okay, if you have a structure like this, a mathematical object like this of n numbers, and these can be real numbers. Now you can imagine all possible n vectors like this, right? And they would form a set. What is a set? Yeah. In mathematics, what is a set? Well, just a collection of stuff. If you ask what stuff, that depends on you. You are free to define whatever you want. It could be a set of your shirts. That's a set. It could be a set of real numbers, for example. The real line, all the points on the real line, they form the set R. So when I wrote R, this R is really a set. And what is a set? Is a set of? It's a set of all possible real numbers. Okay. So if you consider now all possible n vectors whose individual elements are real numbers, that has a representation as well. It's essentially written like this: R power n, which means that each element of this set is an n vector. Okay, a bunch of n real numbers. Okay, let's look at some examples. Let's say we're talking about R2. That means this is a set whose elements have two real numbers. Okay, and the position matters. For example, does this belong to R2? This is a two vector, right? Because there are only two elements. Yes, this belongs to R2. With this. Does this belong to R2? Well, it does not, because it's got three numbers. So this is not from the set. What about number 6? No, this also does not belong. But this. Yeah, okay. It's easier for me to write J. What are these? Yes, complex numbers. Does this belong to R2? No. Why not? Well, yes, these are not real numbers. These are complex numbers. That means it's not in the set. Okay. So that's essentially what Rn is about. Okay. Now, earlier we saw a nice geometric picture for R line, right? You could ask, well, is there a geometric picture for Rn then, right? Is there something that we can associate? It turns out you can, right? Well, for R2, well, R2 has two real numbers. That means there are two real lines, right? You can think of it like that, right? And I can, let's say I have two real lines, R2, because there are two real numbers. Let's say this one corresponds to the first real number, V1. This corresponds to the second real number. Okay. So if this is, let's say, so we choose arbitrary 0, and then maybe this is V1, V2. This is a reasonable representation, right? Now, if I have Rn, I simply draw a bunch of n lines, and I simply mark them one after the other. This is a reasonable thing to do, given that we started with something like this. R is like this, then R2 is like this, R3 is 3 lines, Rn is n lines. Even though this is reasonable, it turns out it's not very useful. Okay, a more useful way to visualize Rn is you draw the first real line, and you draw the second real line perpendicular to the first line. Okay. Okay, and wherever they intersect is where the zero element is. It's just that what is the zero element? So for R, the zero element is simply 0. What is the zero element for R2? Or what do you think? Well, 0, 0 is a reasonable guess. And that's it. That's the zero element. And that's here. Now, if I gave you 1 and see this, I want to look at this point. And now here. Earlier, this line was my entire space. As far as if you're a being that lives in R, you know nothing about anything outside this line. You only, your universe is this line. But if you're somebody who resides in R2, this entire plane is yours. You know anything? You don't know anything outside of this plane, but within the plane you can move. This you're aware of, or this you're capable of perceiving and moving around in. If I asked you where does this reside, uh, what would you say? This point, 1, 2. Yeah, where? Let's. Well, you should still ask me that thing. But what is the scale? Where is one along this real line, and where is one along this real line? Well, let's say I tell you this. These are ones. Okay, and we'll assume that the horizontal one corresponds to V1 and the vertical line corresponds to V2. So this is V1, V2. Now you can locate where 1, 2 is. Where is 1, 2 now? Here. So this is where 1, 2 is. What about well 1, 2, 3? That's -3, 4. That will be here, and so on and so. If I give you a point here, if you had a ruler, then you can exactly tell me what the number is corresponding to this point. Okay. And another thing that we will do is we won't think of these elements as simply points. We will think of them as pointed arrows. Okay, pointed arrow where the base of the arrow is always at the origin. Okay, and the tip of the arrow is at the point that we are representing. Okay, for example, this would correspond to this. Okay, -3, 4 would be. From now on, whenever we talk about n vector, you always think of an arrow in some high dimensional space. In R2, we can draw R3. If you're talking about R3, and let's say this is the origin, this is V1, V2, V3. If I say 1, 1, 1, and let's say this is the size of 1, then the point, it would be an arrow from here to here. Okay? So all points, now we associate an arrow pointing in an arrow of a finite length pointing in some direction. Those are our n vectors now. Okay, all right. There again, a couple of definitions you'll need to remember. We can ask what is the size of an n vector. Okay, when we say size of a vector, we're talking about essentially n, the number of elements there are in the vectors. For example, tomorrow if I ask what is the size of this vector v, and if it's from Rm, then the size is n. Okay. So this is how we will represent multidimensional information, a bunch of numbers where the order matters. And this is the geometric picture associated. We can visualize still R3, but if you have, let's say, something in R10, you simply assume that you can see it and that this vector that you have is pointing in some direction. Many of the geometric intuitions that we have from R2 and R3 will still apply there, even though we can't visualize it. Okay. Okay. There are some important n vectors that we will often come across. Okay. And nothing before I move on, note that R2, R3, they're all completely separate sets. They have no relationship to each other. Okay, that's an important thing to remember. Because later on, when we talk about subspaces, R2 is not a subspace of R3. R2 is a completely separate space from R3. Okay. So some important n vectors. The first one is, of course, the zero vector. Well, for now, if I'm not stating anything, let's assume I'm talking about n vector, n elements in them. So this is essentially a bunch of zeros. That's the origin of this n-dimensional space. And then you have the one vector. This is simply a bunch of ones. Okay, we are defining these because these will come in handy later on. Instead of me telling, oh, consider a vector of ones, if I simply say one vector, you know what that means. Okay, and a really important one are the set of unit vectors. Okay, The unit vector, if you're talking about unit vectors from Rn, there are n unit vectors. So there are there are n unit vectors in Rn, and the ith unit we will always represent. We will use the symbol e for a unit vector. This tells you it's a vector. The ith unit vector is simply a vector like this. It's got all zeros except for the ith position where it's 1. So you have zeros, you have 1. This is the ith position. Okay, so E1 will be 1, all zeros. En will be all zeros and then 1 here. Okay. So with that, we've covered how we will represent multidimensional information, at least for now. Well, representing alone is not enough. Okay, we eventually want to be able to do stuff with these representations. It turns out there are two useful operations that you can do, called scalar multiplication and then vector addition. Okay, again, things that you are familiar with from maybe physics and stuff, but we'll anyway cover it. Scalar multiplication operation is simply this: you take a vector v from Rn. So whenever you see a weird-looking e like this, it means simply replace this by is in or belongs to. So v belongs to Rn. That's how you read it. So I take a vector v from Rn and n vector, and I take a real number alpha. So alpha belongs to R. That means alpha is the real number. Okay, I'm allowed to do this. Mathematically, I'm allowed to do an operation like this, which is actually which is a well-defined operation, where you say you are multiplying the vector v by a scalar alpha. A scalar simply means a single number. Okay, essentially a number from R1, C1, whatever. So we've not covered this, but C represents a set of complex numbers. Later on, we'll see that you can have vectors where the elements are complex numbers. That means in that case, your space would simply be Cn. Object that has n complex numbers as its entities. Okay, right. You take a vector and a real number. You're allowed to do this operation, and algebraically, this corresponds to, you have alpha multiplied by v1, v2, vn. What you do algebraically, you simply take alpha and multiply each of the elements by alpha. So alpha times v1, alpha times v2, vn. Okay, let's do an example. Let's say I have this, right? Let's say I multiply this by 4. What n vector will I get? What 2 vector will I get if I scale this by 4? Well, 4 and 8. What if I scale this by pi? Pi is the real number. Well, it'll simply be minus 3 pi and 4 pi. That's all. Okay. Okay. Now, if this is v, okay, if I multiply it by a scalar, I get another n vector. Right? Each one of this is real. See, v is a real number, alpha is a real number. If you multiply two real numbers, you get a real number. That means all of these are real numbers. That means this is also an n vector. Okay. If it's an n vector, maybe there is a corresponding geometric picture for the scaling operation. What would be the corresponding geometric picture if you scale by 4? Let's say this is my v, and I scale it by 4. What would be, where would be this vector? Yeah. So okay, take a guess. Well, we don't have to take a guess. You can exactly tell me where 4 and 8 is. Where is 4, 8? Right. It's along the same direction. Right? Except it will be now 1, 2, 3. It will be somewhere here. This vector is now 4 times v. So all you've done, so when you say you're scaling a vector, right, by alpha, all you're doing is you're taking the vector and then stretching it by that alpha amount. Okay, if alpha is positive, you're stretching along the direction in which the arrow is pointing. But if this were -1, right, then this will be -1, -2. Then the vector would be in the opposite direction. It'll be here, right? If alpha is negative, then you're simply flipping the direction and stretching it in the opposite direction. Okay. So vector scalar multiplication has a very nice simple interpretation where you're simply stretching your vector. What will happen if the magnitude of alpha is smaller than 1? What are you doing to the vector? Yeah. Yeah, we're shrinking it, right? If alpha is less than 1, you're shrinking the vector. If I make alpha 0, then I'm simply annihilating the vector to go to the origin. Okay. All right. So that's the geometric picture for scalar multiplication. Okay. Okay. Vector addition, on the other hand, involves two vectors. Okay. Let's say we take two vectors, v1 and v2. And well, let me not call them v1, v2. We call them u and v. Okay. U is simply u1, u2, un, and v is v1, v2. Vector addition operation is an operation that takes two vectors and returns another vector. Okay, you write it like this: v1 plus v2. This is the addition operation. And all you do is you simply add the individual elements of the two vectors with the corresponding, which have the same index, right? So this will simply be u1 plus v1, u2 plus v2, un plus vn. You are adding two real numbers. That means this itself is a real number. That means this is also an n vector. Okay, so this also belongs to Rn. Okay, we look at the geometry associated with this. Let's say, let me write it down. Let's see, 1, 1. Okay, those are the two vectors, and let's say this is 1. Where is u? Well, u is here. V is here. So this is my u, this is my v. If I add those two, what do I get? If I do v1, u plus v. Yeah, you'll have to be louder. Yeah, you get 3, 1. Where is 3, 1 here? This is 2, 3. That will be here. This is the odd. Okay. What did we do geometrically here? We had u, we had v, but how did we get this u plus v? You remember the parallelogram law of addition of vectors? What do you do if you want to add two vectors like this? What did you do when you had to apply the parallelogram law of addition of vectors? Well, it's very simple. You fix one of the vectors. Okay, you take the other vector and you simply move it along the other vector until the base of this moving vector sits at the tip of the first vector. Okay, you take this and you move it along, and then you simply then join the base of the first vector and the tip of the second vector. It doesn't matter which vector you choose. Okay, I could have fixed this and then I could have moved this up, and I'll get the same result. Okay, and the reason it's called a parallelogram law of vectors is if you have two vectors like this, if you draw a line parallel to this line from the first vector and draw another line parallel to this line from here, the point where they meet, this forms a parallelogram. The addition of through these two vectors is the main diagonal. Okay. So this algebraic operation of addition of two vectors simply corresponds to applying this parallelogram law of addition of vectors. Okay. Yes. So those are the two major operations that we will look at. I mean, of course, you can say, well, can't we have other operations? Where you say, okay, I want to multiply two vectors, and you're going to represent it like this, not the cross product, but some multiplication operation. And you could say, well, I'm going to define it as multiply u1 v1, u2 v2, and so on. You can. It just turns out that this is not really that useful. I'm sure people have tried, and they've not really seen any major use for something like this. So we don't look at operations like this. But you can, if your application demands that you do something like this, you can do something like this. And in fact, there is, you can actually do something like this. It has a name, but this is not something that we will often come across, at least in this course. In applications in neural networks, you might come across this type of a product where you want to multiply stuff element wise. In fact, MATLAB has an operation where you can multiply stuff element wise. But in linear algebra, we really don't have any use for an operation like this. Okay, so with those two defined, we will now look at maybe the first most confusing concept. The concept of a vector space. Okay. It's happened before that students of the course don't know until the end of the course what a vector space is, which is unfortunate. But you have to know. If you don't know this, you don't know the rest of the course. So please make sure you learn by heart the definition and you blindly apply it wherever it's necessary. Okay. And it won't make sense at all initially. Okay. See, so far we've looked at R, we've looked at R2, Rn. Okay. All of these were sets. Okay, just a collection of stuff. Okay. A vector space is also a set, simply a collection of stuff. Okay. But if it is just a collection of set, you'd simply say it's a set. You won't call it a vector space. For a set to become or to be called a vector space, it needs to satisfy a couple of properties. Okay. So whenever somebody tells you vector space, what mathematical object does it correspond to? It corresponds to a set. It's simply a set, collection of stuff. A set with special properties. We look at what those special properties are. There are two of them. Two properties. Okay, and both these properties have to do with the concept called closure, which simply deals with whether or not something is closed. Okay, and what that means is this: if you have a bunch of stuff, right, and let's say you've defined some operation that you can do with this bunch of stuff. If you take some elements, do that operation, and if the resulting element from that operation also belongs to that set that you started with, and it belongs to that set no matter what elements you choose for doing this operation, then you say that the set is closed with respect to that operation. Okay, maybe that's already a mouthful, but we'll look at some examples. Okay, remember this: we were talking about the set Rn, and then we talked about this operation called scalar multiplication, and we defined scalar multiplication to be like this. We represent it like this: a scalar placed before a vector v, and the corresponding algebraic operation is you take the scalar and multiply the individual elements of your n vector by that scalar. Okay, so you started with the vector from Rn, and then when you do this operation, you get another n vector, and it turns out the individual elements are also real numbers. That means the resultant of the operation also belongs to Rn. And no matter what v I choose and what alpha I choose, as long as alpha is the real number, the result of this operation will always be in Rn. Okay, that means at least in terms of scalar multiplication, the set Rn is closed with respect to scalar multiplication, which means that there is no scalar multiplication operation I can do that will take me outside the set. So I'm free to do whatever I want as far as scalar multiplication is concerned. I will still be within the set. Okay, that's essentially what closure means. Now look at this. Is Rn closed with respect to vector addition? Based on what I've just said, see if you can argue to find out whether or not Rn is closed with respect to vector addition. If yes, you have to explain. If no, you still have to explain why you think it's not closed. Is it closed? Or at least MS students, what do you think? If you think it's closed, raise your hand. If you think it's not closed, you can raise your hand. Closed? Okay, 1, 2. Maybe raise your hand, it's easier than I know. 2, 3, 4. Why is it closed? You're not sure. Okay, let's start with you maybe. Why do you think it's not closed? No, sure. Okay, you guys thought it was closed. Why is it closed? Yes, here. The way it's, again, look at how it's defined. Addition of two vectors is simply you simply add the individual elements of the vector. If you add two real numbers, it's a real number again. That means the resulting vector will have a bunch of real numbers, which means it belongs to Rn because it's a vector with a set of real numbers. That means it's also closed with respect to vector addition. That's the property of closure. Okay. Now, if a vector space is closed with respect to one scale, sorry, I should not say if a set. I should not say if a vector space is closed. If a set is closed with respect to scalar multiplication and vector addition, if it's closed with respect to these two operations, then that set can be called a vector space. Okay, that's all. Okay, and this is all you have to remember. I give you a set. Let's say I give you a box, and I define two operations that you can do with the elements in that box: scalar multiplication and vector addition. I can define them. I can define them to be arbitrary operations. They don't necessarily have to be the multiplication and addition operations that we are used to. Okay, this could be anything. Okay, I define these operations and I ask you: is this set a vector space? Let's say you have infinite patience and you can check each and every possible scalar multiplication and vector addition, and you check that and you see that none of the elements that come out of these operations actually goes outside the box or does not belong to the box, then you say yes, that box is a vector space. Okay, that's all. So that also means Rn is a vector space. Okay, because it's closed with respect to these two. Okay, one consequence of this, these two are enough to define a vector space. The third one, which is actually useful to remember, is a vector space will always have the zero element. Okay, zero must be present. That is obvious because if you take alpha to be 0 and you do scalar multiplication, and if it's closed with respect to scalar multiplication, 0 has to be in that set if it's a vector space. Okay, so tomorrow if somebody gives you a set, the first thing you look for is ask, is there a zero element? If there is no zero element, then you know it's not a vector space. Okay. 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 That's all the time we have now. We'll stop here and then we'll continue from tomorrow morning. Yeah. Okay. We'll